Well, I want to thank the organizers for inviting me to speak here about our Exascale project. I'm going to go over at a fairly high level of what we're doing, and actually hope that this is an opportunity to get some folks, to make some connections with some of the folks in the audience, both from the vendor side, also from the application side as well. So Exalearn is actually one of the last projects set up, certainly one of the last large projects set up in the Exascale computing project overall. There was a realization that probably more could be done in machine learning in ECP, and so it was sort of a top-down decision from the ECP leadership, and it involves 8 of the multi-purpose DOE laboratories. So I'm the PI, Frank Alexander from Brookhaven, but it's really a partnership with 8 national labs. So it's Brookhaven, Argonne, Lawrence Berkeley, Livermore, Los Alamos, Oak Ridge, Pacific Northwest, and Sandia National Labs. And it's been a real pleasure to work with folks from all of these labs. As I was saying to someone earlier, we're going to compete with the same set of individuals in a lot of machine learning projects quite vigorously, but it's nice to at least have one project that we're working on really together. And like I said, it's been a real joy so far. See me in 3 or 4 years, I may say a totally different thing, but I think for right now, no, it's been a real joy. So we've been up and running since about September of last year, so it really hasn't been that long at all. So let me just explain what we mean by co-design. It's sort of a multidisciplinary collaborative process. It's certainly an overused word. In co-design, systems are developed with the application software influencing the hardware design trade-offs. And I think, quite often, a lot of the hardware is already baked in, so there's not a lot of degrees of freedom by the time we get to a project at this point. But the idea would be to influence, given the particular problem you want to solve and the particular types of algorithms you want to use, in this case machine learning, variety of machine learning algorithms, which I'll go over, how would you design the algorithms, design this, the remaining degrees of freedom of the software, the hardware, and so on. And it really encourages all parties, from the system designers to the architects to application software tool developers to our DOE, our significant and large set of DOE experimental facilities, et cetera, to try to design and optimize the system to solve particular problems. So there are 6 co-design centers, and Mike Haru gave a talk earlier today where he spoke about the larger ECP structure. So I'm not going to talk about that at all, except to say there are 6 co-design centers. We were the last one formed. They range on data analysis and reduction, particle methods, adaptive mesh refinement, discretizations, graph methods or combinatorial methods, and finally for machine learning. And they really span all of these centers really are focusing on technologies that are used across a huge swath of DOE applications. And so we're focusing on machine learning, and at the end I'll show you some of the other machine learning work that's going on in the ECP project overall, though. We're also happen to be in a topical area that is, as you heard today, you'll hear tomorrow, and you will know anyway, a very rapidly changing area of machine learning. So while there's a lot of work that goes on in discretization and still a lot of work in particle methods, the pace of new developments in machine learning has just been, I was going to say astronomical, but I was taught by Dan Jacobson today that it's biological, I guess, so it's not let me skip this, I guess. So we're looking at machine learning in a couple of different contexts. We're looking both using machine learning to enable high-performance computing, and then also machine learning which benefits from high-performance computing. And so it's really, and actually in all of these projects, there's a little bit of each. So it's not just saying we have this massive data set we want to analyze. We're looking at, how do you generate that massive data set efficiently using machine learning and exascale resources. And so it's really coming at it from 2 different sides. We're looking at a variety of different methods, and the methods are being dictated by the applications that we have in mind, that we've targeted, and I'll explain some of those. I'll explain those to you later. Deep learning, of course, is all the rage. You've heard a lot about it already today, and certainly deep learning is a major component of the work that we're looking at, of the algorithms that we're looking at, convolutional neural networks, recurrent neural networks, and so on. But we wanted to make sure that we didn't just focus on deep learning, because there are a lot of other outstanding machine learning methods, a lot of machine learning methods out there, for which there is actually very strong mathematical foundation and understanding. Deep learning is really only beginning. It's great. It works where it works really well. We need to understand that better, but we wanted to make sure we're looking at we're not just focused on one particular type of learning. So we're looking at ensemble methods, random forest methods. We're very interested in reinforcement learning. I'll talk about a project we're looking at with that. Kernel methods, tensor methods. Again, these are very well founded mathematically, and then also graph-based learning. And this makes connection to some of the other ECP projects as well. So the overarching goals of this project are to provide exascale machine learning software that could be used by a variety of different entities. So, for example, our biggest user base would be other ECP application projects, and you'll see some examples of those. Other ECP Co-Design Centers, so there's a really nice synergy between what we're doing in Exalearn and what, for example, what CODAR is doing, which is a project led out of Oregon, but involves other labs as well, on data reduction and analysis. We're particularly interested in making connections to our experimental facilities that I alluded to earlier. In particular, the DOE runs a number of light sources, so for scattering and so on. Brookhaven has one, but also Oregon, Berkeley, I know I'm missing one. Whoever's represented that lab of the light source that I'm missing, my apologies. SLAC, I'm sorry, for the LCLS. And so, you know, there's and at Oak Ridge also for the spallation neutron source. So there's a tremendous interest on the experimental facilities leveraging machine learning capabilities to help them do their experiments better. And then finally, using machine learning to impact our leadership class computing facilities themselves. And so, like I said, this is a multidisciplinary collaboration that also couples to the application development projects that Mike alluded to earlier, and some software technology projects, but also to the vendors as well, to the PathForward interactions. So when we were scoping out what we wanted to do, we decided to go with, you know, we wanted to choose problems that, or choose machine learning methods that apply to multiple problems within the DOE mission. So not just that will only work on that problem. Now, it's not hard to find machine learning methods that work across a whole suite of problems, but that was something we wanted to make sure we included early on. It has a line of sight to exascale computing. As I mentioned before, this is either because the learning process itself requires exascale resources, and or the generation of the data requires exascale resources, or you're actually influencing an exascale machine. So there's a lot of different ways this can come in. We don't want to replicate capabilities that are obtainable from widely accepted packages, in particular what's happening in industry. In fact, we want to leverage those to the extent we can, and other projects are doing that as well. Being in the Department of Energy and not at a, you know, in an industry where the goal, say, is to discriminate between cats and dogs or label images, not to say that that's an easy task. We are we're dealing with physics and biology and chemistry problems and climate and other problems about which we have a considerable amount of domain knowledge. It may be imperfect, but we actually do have a lot of domain knowledge about these systems. And so the idea is, how do you, the challenge is, how do you build in as much of this domain knowledge as possible to help build better machine learning or AI algorithms? It's not hard to, I mean, you could always apply it with, for some of the problems, they're so complex that if you were just to leave it up to the data that you had available and or the limited computing you have available, after all, everything is limited, the problems would still be too complex to solve. So you really want to bring in, we really want to bring in as much theory and as much understanding of the problem as possible, even if it's imperfect. And then not unrelated to that is the quantification of uncertainty. So we want to be able to make predictions, and you saw that in some of the examples earlier today. We also want to be able to quantify our uncertainty in those predictions. So how confident are we in those predictions? Can we back that up? And that's a very exciting area that the DOE has been a real leader in at multiple labs. We'd like to deliver a product that, where the actual algorithm, the machine learning algorithm that's learned is interpretable, not unlike what Dan was talking about earlier today. So that's very important for us. We don't want to just have it as a black box. And then we also want it to be reproducible, because that actually turns out to be, more than I had appreciated, a serious issue in a lot of machine learning research. So those were the criteria that we applied to, deciding what we wanted to, what we were going to limit or work on given our limited resources. I'll leave this slide up there. I don't want to go through all of this. And the reason I want to leave this up here is because we have a set of apps. So I will describe to you 4 machine learning algorithms that we're working on now. We have a set of applications, targeted applications for each of those. But we're in the process of thinking, what are we going to do after, what are we going to do in our second year and a half? And so actually this is a great audience to talk to about this. We're looking for next applications. And so, if you look down the list, those are some of the criteria you're using to actually select the applications. Would it enable new science? Is there a specific science question we're trying to answer? Do you have examples do you have examples in hand that we could benchmark now? That's very important for the Exascale project. What are the performance considerations? Do you want to work with us? I mean, we can provide a lot of the resources, but if, ultimately, what we can't do is say, here, go figure this out. It needs to be a partnership. And so we're very excited to find the next set of applications, and I would encourage you afterward to come up. If there's any interest, please let me know, or let folks from the various other labs know as well. So I'm just going to briefly describe at very, very high level the 4 types of machine learning algorithms we're developing at Exascale. The first one is using machine learning, and in this case particularly a lot of deep neural networks, variational autoencoders, and so on, for developing surrogate models for very complex simulations. So in the DOE and other places as well, we make these very large simulations of, in this case, cosmology, of the universe. Doesn't get any bigger. So sorry, biology may be more complex, but it is smaller. So we carry out these incredibly expensive n-body simulations of the universe and its structure, or very large-scale climate simulations, or very large-scale high-resolution plasma simulations in a tokamak. And what you'd like to be able to do is replace the very costly high-resolution simulations with a surrogate model that is actually a lot cheaper to compute on, but nevertheless preserves the physics or chemistry or biology or whatever that you care about. So there's a lot of work in the mathematics and applied math in this area, but one of the sets of tools that seem to work quite well these days is a variety of deep learning algorithms. And so we're adapting that to be able to our first cut will be applying this to very large-scale cosmology simulations. We are looking toward next applications. It could be that it's tokamak plasma. It could be climate. But if any of you folks are interested in suggesting other things, I'd be more than happy to listen. Actually, I should say that one of the things we're developing in this cosmology surrogate is extending the software from 2D convolutional neural networks from 2D to 3D, and then eventually, hopefully, to 4D. So that's turning out to be a real challenge, but that could be applicable in a lot of places, especially where time series matters. Again, not unlike some of the stuff Dan talked about. So the second application area, very different. This is focusing on the experimental facilities that I mentioned earlier. We're very interested in looking at machine learning for control. So in particular, and this is a pretty generic question, how can if I'm carrying out an experiment and I can tune some of the parameters in the experiment, so I can change the temperature or the electric field or whatever, the pressure in an actual experiment, how can the experimentalists tune those in real time as they're getting data off the experiment, so that they can, the case we're looking at here, that you can grow a block copolymer into a particular structure. And so block copolymers, I won't go through all the physics of block copolymers, but there's a tremendous interest in these really cool things. They're basically polymers which have one type of monomer at one end of a certain length and another type of monomer at the other end. And when you change the temperature, the field, et cetera, these things can grow into some really fascinating structures. And it turns out that one possible application of this is for constructing very small-scale electronics, using those as a template on which to grow, use more traditional deposition methods. And so the idea would be, can we take an experiment running at a light source? The one pictured here is, let me see if this works. This is the light source at Brookhaven. As an experiment's being carried out, can we have simulations of this process that's going on? We have a model for the process that's perhaps and almost certainly good, but certainly incomplete. As the process is unfolding and as you're getting data from this, can you tune the parameters under your experimentalist control to guide this thing to grow in a certain way? And so, as it turns out, this is a very nice. We believe it's a very nice application of large-scale reinforcement learning using things like deep Q learning and so on. And so, this will give us an opportunity to go in a totally different direction, let's say, than the first problem I talked about, which was building surrogates. And so, as you can see, you've got the idea is to have this workflow that you've got a simulator carrying out real-time simulations of the thing as it's unfolding. You're getting data and using reinforcement learning and things not unrelated, say, to common filters or controllers. How do you change the temperature in real time? But at the same time, you've got a very complex simulation of this process running. And we're connecting to other projects in ECP, in particular the Exalearn, or Additive Manufacturing, or Advanced Manufacturing Project, which is led out of Oak Ridge. So So actually, this is the case. This is the problem we're starting with. Ultimately, though, where we think this will go, it will actually, we believe it'll leverage some of the tools developed in the first project, because in the end, we're not really going to be able to simulate these high resolution, carry out a simulation of high resolution of these dynamical processes of phase transition kinetics with any level of fidelity. Using the bare model that we have now. Ultimately, we want to do is build a surrogate model from that. And so we could easily imagine in a workflow, you build the surrogate model first for this using tools from the first example I gave you for this particular project, and then apply that in this reinforcement learning context. And so there's we think there's a huge potential set of applications for this in any optimal control of experimental facilities, but other things as well. And so it's like I said, it'll allow us to build technology, machine learning technology for things like reinforcement learning, which has done extraordinarily well in a lot of contexts recently. The third problem area we're looking at is looking at machine learning for inverse problems. And so the idea there is to use, be able to go rather quickly from an image that comes out of, say, a scattering experiment without solving a very complex inverse problem the way it would normally be solved. Can we infer something about what generated that image very quickly by training something in advance? In particular, there's a lot of different the kernel methods, tensor methods, but also possibly deep learning methods there as well. That's a huge problem, again, in DOE space, whether it's images coming off of a scattering experiment at a light source, or it's time-dependent stuff coming off of seismic signals coming out, being recorded and trying to infer what was the origin of those seismic signals and so on. So inverse problems are also, and then again, that's another area, not unrelated necessarily, and we could start imagining how to stitch these things together, the tools from different things, but it's a different application area. And then finally, let me skip that. Finally, one of the I think maybe the most ambitious thing we're looking at is this idea of using machine learning for optimal design. And so in particular, and this is being done actually, there are already a lot of projects in the DOE that are looking at things like this, but we want to really take it to Exascale. And so basically, if you wanted to find a material with certain beneficial properties, can we use methods from, say, reinforcement learning or other types of learning algorithms to quickly give the experimentalist an idea of what they should be looking at, so you can test something there and quickly discard options that are likely to not to succeed. And so our first two use cases there are going to be in electrolytes and in catalysis. One of the things we care about is obviously scaling and performance, and so that's, we need to have classification, regression, and deep learning models that scale and perform very well. Same for reinforcement learning, and an important component, especially as we start to stitch these things together, is the workflow that we're setting up so that you can actually do a surrogate, apply the surrogate at a light source, and so on, take the results of that, and then solve an inverse problem, for example. And so those are cross-cutting areas. A certain fraction of our project team are working on those areas as well. What I want to mention here is, as I said, we're not married to a particular framework or tool set to begin with. We're exploring a number of things: TensorFlow, PyTorch, LBAN, and so on, and some of the stuff that's being developed in the Candle Exascale Center. The idea was not to narrow it down initially. I have a feeling, we'll see how at the end of a year of this project where we are, and if one of the methods really just stands out, one of the tool sets stands out to be superior to the others, then we'll probably go with that. But we're still very early stage and couldn't really nail that down yet. A recurring theme that throughout all of these things is what I would say is what I call is objective-driven experimental design. An experiment doesn't necessarily mean a physics experiment or an actual physical experiment. It can also be a set of simulations that you carry out. The simulations can be very expensive. And so how do you decide what to simulate? So in particular, one of the problems we're looking at in the surrogate case is, rather than just say, I've got a bunch of data that came off of a simulation all the simulations I did of cosmology or that type of universe model, and I want to use that to come up with a surrogate model, we think a better use of resources would be to decide what you want the surrogate model to do well, or actually any of these things. What would you like the inverse problem, what aspect of the inverse problem would you like to solve well? What aspects of control do you want to perform well? And then go back and say, given that information, we're trying to build a tool set that says, okay, given that and your knowledge of the system, here's the set of simulations you should go carry out in order to do that. And so it's not just blindly taking the data that you have. I mean, that's fine if you have it, but I think for a lot of these things, you're going to have to be generating new data, and we think that's a resource limitation as well. So anything you can do to help narrow down to narrow down what simulation should be done can be very valuable. So DL Hub is a data and learning hub, which is work being done out of Argonne. This is something that we will also be integrating with, and this is a way to share a variety of, and publish and share a variety of data and machine learning models across a variety of different applications. I could certainly give you more information about that. That's a project led out of, as I said, out of Argonne by Ian Foster, who's on our team. A lot of vendors here. So one of the important components of our project, and actually of all of the ECP projects, is PathForward or vendor engagement. And so Michael Wolf at Sandia and Jim Ang out of P&L have been leading those efforts with a variety of companies, as I said, probably all of whom are represented here. And so in addition to the vendors, we're also looking at engagements with our experimental facilities across the DOE lab and so on. So again, if there's any interest on the part of vendors, I'd be more than happy to talk with you about that and also to point you to Jim and Michael. Almost done. And so I did want to mention there is another ECP project called Candle. It's actually an application development project. This is led by Rick Stevens at Argonne, but involves Los Alamos, Livermore, and Oak Ridge as well. And they're really looking at a lot of deep learning methods, specifically focused on cancer. And so there's been a lot of nice synergy between that project and our project, especially since we have a lot of the same people working on both of those. So I wanted to mention that there's already another, and this project has been going on for almost 3 years now. So there's an ECP Exascale machine learning project already out there that's fairly well developed. And with that, I want to thank you. We have a few minutes, so any questions for Frank?
Machine learning is the hot topic. I thought people would be all over this presentation. All right. Steve is going to ask this.
At least in relation to what you're doing, could you talk about the status of deep learning and whatever else is associated with like neural networks and so forth, the sort of the supporting technologies?
So are you asking, are we doing any R&D on the
I'm just saying how much effort is needed to just kind of evolve the deep learning technologies, the kind of the software things like, convolutional neural networks and so forth.
Right, so I'll try to answer your question. I may not be answering the question yet. This is really a software development project, so we're not really focusing on changing any of the algorithms. There are a lot of algorithms out there now that work reasonably well in the areas that they work in. Like I said, some of them have mathematical foundations and some don't. Okay, so from my personal research point of view, I'd much rather be focusing on the development of the algorithms and applications, but this is so sure. Any other questions?
I have a question.
Yes, okay.
So since you have been heavily involved in machine learning and deep learning, what is one myth about deep learning or machine learning that you want to bust today?
So I know one, I don't know if it's a myth among this crowd, but I think, and it goes back to one of the, it goes to one of the slides I showed earlier. Deep learning is not going to answer every question. I want to repeat this because it works really well discriminating cats from dogs, or actually works really well in natural language processing and a lot of other areas. But for a lot of the problems that we really need to solve, in my opinion, the problems are so complex, and relative to that complexity, the data is so sparse, even though there may be a lot of bits, that I don't think you're going to deep learn your way out of things. Now, I think you can use it as a way to guide intuition. I think Dan actually showed some really nice things. It was a way to say, okay, that looks interesting. Maybe we ought to think about that. So I guess I don't think there's any replacement for theory for a lot of the problems we want to solve. And so one of my fears, I guess, is that so much is being invested in the hardware and in the algorithm, the deep learning algorithms, without doing two things, without investing a concomitant amount in the understanding of the mathematical, what's going on in these deep learning algorithms. The other methods have a lot of good foundation, as I mentioned. The other one isn't just development of theory. I don't think there's any substitute for any of these problems for having a good theory of the early universe, even an imperfect one. Or, as Dan said, there's the biology problem. It can't all be data driven. So that's my very convoluted way of trying to answer your question. So.